Hello everyone, welcome back. So today we will see, in this video in fact, we will see something on the residual analysis. We'll look at something called as error analysis. To do that, let me just start by sharing my screen with everyone. Okay, I will follow the same methodology. I will use MATLAB as a tool to show you the results. What I'll do is I'll do regression basically. I'll do nonlinear regression. And based on nonlinear regression, I will try to discuss a few things on error analysis. So this is again in one of the previous videos I showed you how to do linear regression and nonlinear regression based on some library. I showed you two methods, LMS and KMCC methods. Basically, these are all the methods that I have in my my library, with my MATLAB. All these methods are implemented in my MATLAB. In one of the previous videos, basically we tried to do some nonlinear regression, and we found out hyperparameter tuning helps in minimizing the error. Moreover, it helps in minimizing the the overall error curve. Let me show you what I'm talking about. The overall error curve. This is the overall error curve. With time and with more training samples, the error value should go down. But reality is, if you have like tens and thousands of nonlinear regression methods. The problem is which one to select, and that problem basically is like model selection problem, and there is no alternative. You have to do some either you have to test a few things, you have to try a few things. One model, let's say this model is giving me an error of 0.0089. Let me try one more model. Let me try this model, a QKLMS model. Let's see the error value that I get is like 0. Let's take the same parameters. Let's see if we get, I'm hoping we get the same result. Yeah, I was right. Let's see another method. Let's see this kappa method. 0.6, let me just fine tune it. Very bad. I think that's it. Let's try tuning. I don't know. Maybe we'll get better result. No, I don't think so. This is the best result that we are getting using this kappa method and using this QKLMS or KMCC algorithm in this case with the error value, specifically the error value that we got was 0.0089. Trying different algorithms, we saw again this KAP is also a non-linear algorithm. This QKLMS is again a non-linear algorithm. Quantization implemented into it, but again and this KMCC is again one more method. In this case, quantization method and KMCC revealed the gave me the exact same results. There are multiple reasons why. I will not get into the reasons why we got the same result. And again, if you understand what is meant by quantization, looking at this parameter value, looking at the length of my my data, nothing but 546, you can understand why we got the same result. But let's not get into that. Let's assume that we have two models. One is KMCC, kappa, and let's take one more. Let's take this linear method, LMS. Let's do something. Let me show you the result for that method as well. Okay, 0.0159. Okay. So now I know that, let's say my real values, I know is nothing but y. Predicted value I know is nothing but y underscore estimate. Now let me compute the error values. Error is nothing but my real minus predicted. Let's say. Now let me look at my histogram of error values. And let me just fine tune it. Let me pass like 50, I don't know. Yeah, okay, nice. Now let me open up my paint window that we can analyze this thing better. Let me just minimize it. Let's take a screenshot and let's paste it here. And let's crop a few things. This is my linear method, by the way, my LMS method. And now let me just change the mode KMCC. And let me do the same thing. Real is equal to y, predicted is equal to y underscore estimate. Error value is nothing but real minus predicted. And let's repeat the same exercise. List of error, 50. Let's take a screenshot and let's, okay, just give me a minute, just give me 1 minute. And here we go. And let me just do one small thing. Let me just write, this is like linear. It's not working. Again, let me try it again. Linear method. This is non-linear method. Again, I know I'm abusing the terminology here, but again, let's just assume it that it's right for the time being. This is my M1 and this is my M2. Okay. Now everything is between 0 and 1. The original data was between 0 and 1. Now let's compare these two graphs. Here I can see that these two graphs approximately they follow, something like a normal distribution. I know it's not exactly. Oops, let me take a pencil. It's not exactly a normal distribution, but it looks like a normal distribution. Let me take the color as black. And something that looks like this. Looks like, this. And for this, let's say this looks like this. Oops, like this. Comparing these two figures, let me remove the pencil marks. Comparing these two graphs, okay, I can see that for nonlinear method, majority of my, these are my error values. Majority of my error values, they are concentrated in this region. There are some values here, 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 and here as well. Same way, some values are here and here. What are the conclusions that we can draw, from this? Ideally speaking, the error values, they should be like, in normal curve. Now, a normal curve. Same thing with this normal curve, and that's generally the pattern. The error values, say generally, again, I'm thinking generally, if they looks like, they don't follow, they look like normal distribution. But again, in this case, we can see that it's not normal. There are a few exceptions. See the exceptions. See the exceptions. Outliers, basically. Outliers. Too many things. So ideally, for an ideal model, for a model which is very, very good, what should be the shape of the histogram? Again, let me point out a few things that when we were computing the error, the MSE value for this came out to be around 0.059. Similarly, the MSE value for this came out to be like 0.0089. Looking at these numbers, of course, I can say that this guy performed well. I mean, that's common sense. That's what we do. We just compare the numbers, and then we are based on these numbers. We actually say, okay, model number 2, the non-linear method is good. That is not really good. And that is the question that we'll try to answer. But again, there is no real answer here. But again, we'll try to look at a few things. And as I said, the error values should follow. Again, it's not a rule. It's not compulsory. The error values should follow something of a normal distribution if we remove the outliers. And the next question is, what should be the ideal curve for a very, very good method? These are the few, important questions. Very important questions. And that becomes the foundation of something called as a model selection problem. You have n number of methods. You have SVM, random forest, ensemble maze methods, neural networks, convolution neural networks, LSTM, and all those crap. Then you go to other fields. You have wavelet based methods. You have kernel based methods. You have, I don't know, so many methods. Which method should you choose? That's again a model selection problem. The underlying assumption here is the features. You have selected the features in a very good way, and you are trying to come up with one model. And by the way, that's impossible. If you see, the question also becomes like, for you have n number of data sets, can we find one method that suits, that fits all the data sets? I don't think that's possible. In fact, the no-free-lunch theorem says that you cannot have one model that performs well in all the situations, all the problems, all the data sets. The question is, how can we come up with the real answer? And the real answer, we'll take a look at the real answer in the next video. So stay tuned. Till then, take care. Bye bye.